algebra students. We're going to continue working with our quadratic functions. Remember, quadratic functions are things that have something being squared in them. And today we're going to be talking specifically about falling objects. In science class, you may have already talked about this because this has to do with gravity for a lot of what we're doing today. And we're using this specifically to describe that kind of a situation when we have gravity acting on something. So I want you to start by looking at this table. We're going to be using this table in this presentation. And I want you to think about something that you notice and something that you maybe wonder about in here. So take a moment, you can pause it if you'd like. A couple of things that I have noticed in this table is I noticed that the x's are all increasing by 1, but clearly the y's are not, right? The y's are increasing, but each time they increase, they're increasing by more than they did the time before, right? So this is clearly not linear. We don't have a constant rate of change, but it is growing rather quickly. You might notice that the y values are all divisible by 4. In fact, they're all divisible by 8, and maybe not as obviously, they're also divisible by 16, which will be very helpful with what we're doing today. Something that you might wonder about is maybe what the rule is, what this pattern really is that's giving us these y numbers. We can tell it's clearly not linear, but maybe we could see if this is a quadratic pattern because that's what we're working on. You might be wondering what the next number in the table might be, looking for patterns and trying to figure out what that is. So we have this situation, and this is where those numbers came from really, is this situation. So you can flip back on the first page of this that we had, and you can see this table. We are dropping a rock from the top of a 500-foot tall building. Hopefully it won't hit anything important when it gets to the ground. But you can see from this picture, at 0 seconds, it's fallen 0 feet because you haven't dropped it yet. You didn't let go of it. At 1 second, it has fallen 16 feet. Then at 2 seconds, it's now gone 64 feet, not from where it was at 1 second, but from the very beginning. It has dropped 64 feet. At 3 seconds, now it's dropped 144 feet, right? So you can see this from the picture, and you can even see from those arrows, like the arrows are getting longer each time because it's dropping farther each second. It's accelerating, really is what's happening. So the first question here is, how far will the rock have fallen after 6 seconds? This is kind of a trick question, right? In this picture already, I can see that at 5 seconds, it has fallen 400 feet. But remember, this is only a 500-foot tall building. So there's only 100 feet left. This is more than 100 feet that it fell here. So I know it's going to fall even farther than that during the next second, between 5 and 6 seconds. But the ground is only 100 feet away. So this is saying, how far will it have fallen? 500 feet, because that's how tall that building is. That's as far as it can fall. Once it hits the ground, it's done. So it's kind of a trick question. That's not really how far it would travel. If we had any length here, if we had a taller building, it could fall farther than that. But because it only is a 500-foot building, that's as far as it can go. So Jada has been working on this, and she notices a pattern here. She notices something about the numbers. So the first second, it falls 16 feet and then 64 feet. So we've got all those numbers up here. And she noticed that, like I said in the table, all of the numbers are divisible by 16. So if sorry about the bell, we'll hear another one in a couple minutes. If I consider this first one and I say 16, well, that's really just 16 times 1. And then 64, well, that's divisible by 16, but that's 16 times 4. And then 144 is 16 times 9. And 256 is 16 times 16. And 400 is 16 times 25. I'm hoping that you see a pattern. I know it's right here, but those numbers that I underlined are all perfect squares. It's 1 squared and 2 squared and 3 squared, right? This is what 1 second and 2 seconds and 3 seconds, 4 seconds, 5 seconds. This is 1 squared right there, and that is 2 squared and 3 squared and 4 squared and 5 squared, right? So we can see that pattern. So this is going to be a quadratic function because we have something that's getting squared in there. And it says use Jada's pattern to predict the distance that it has fallen after 7 seconds. So it's skipping over 6 seconds, and that's okay, we can do that. But I want to know how far it is after 7 seconds. And we're saying, let's just assume that the building's actually tall enough so that it could actually fall for 7 seconds, okay? So I know that for each of these, I took the seconds that it has fallen, and I square that, and I multiply it by 16, okay? So I would have 16 times 7 squared. Well, 7 squared is 49, so I'm going to have 16 times 49, and that number is 784 feet that it would have fallen after 7 seconds. So then what I'd like to do here is I want to be able to write an equation that shows that pattern. Right? We know that we're taking the number of seconds and squaring it. They're saying that instead of like seconds using S for seconds, we're going to use T for time right there. That number is getting squared every time. And we know that every single time it got multiplied by 16. So this distance that it's going to fall would be equal to 16 times the number of seconds squared. The distance equals 16t squared. Now that I know that, I can use that to find any number that I want. Okay. Oh, these are just the answers that we just went through. Galileo Galilei, the Italian scientist, he did a lot of work with free-falling objects and gravity, and a lot of medieval scholars did study that. They were looking for those patterns, and they figured out that equation that we just had. The distance that an object falls is 16 times t squared. And again, t is the time. So if an object is dropped from a height of 576 feet, I want to know how far it would fall in just a half a second. So I would have to put 0.5 in for the t. So the distance here would be 16 times 0.5 squared. And remember, we're worried about order of operations, right? You can't multiply first and say, well, 16 times a half, that's 8. And then square that. Sorry about the bell. But here's what we would do. We would have 16. 0.5 squared is really 0.25. It's also 1/4. Times 16 would give me 4 feet. So in a half a second, if I drop something, the fact that it's at 576 feet, that's not really important in this question, but in a half a second, it would fall 4 feet. I don't care what the height is that I start at, that's how far it could fall in a half a second. So to figure out where that object would be dropped, this is that 576 feet that we just had. Elena and Diego both made this table, and I want you to notice the differences here and how they're alike. I know that we have to fill in this table, but let's start with how are the two tables alike? They're both counting time in seconds, but the way that they're different is that Elena's table is talking about how far something has fallen, like how far it has moved. And Diego's table is looking at how far it is from the ground. So Elena's table is starting at the very top of this, and it's counting how far it gets away from the beginning amount, or the beginning height, I should say. And Diego's table is looking at this and saying, I want to know how far it is from the ground. So when it starts, it's 576 feet from the ground. And keeping track of how close, you can see his numbers are decreasing because it's getting closer to the ground, right? So this is going to ask you to fill in the table. And I know you can't really read that down there, but we can figure out this table. Let's do Elena's table first. We're using that same D equals 16 t squared. So at 0 seconds, you put 0 in for the t, 0 squared is 0, times anything is 0. Put in the 1, put in the 2, we've got those first ones done. When I put in a 3, so this is going to be 16 times 3 squared. 3 squared is 9, 9 times 16 is going to be 144. When I put in 4, I would have 16 times 4 squared. 4 squared is 16 times 16 is 256. Right? And we said for whatever time this is, we have it up at the top right there. We're going to say that it's going to be 16 times t squared. That's how we get it. Diego's table is a little different because, again, we're measuring how close it is to the ground. And that's kind of like the reverse of this. So what I would do on this one is, I'm going to kind of use Elena's table to be able to figure this out. If after 1 second it has fallen 16 feet, which I can see from right here, if I did 576 minus those 16 feet, that's how I get the 560. Then after 2 seconds, it has fallen 64 feet. So if I had 576 and I would subtract the 64 that we have right here, that's how I get the 512. That's what I'm going to keep doing to get the 3 and the 4. So if I had the 576 and I subtracted away the 144 feet that it has fallen so far, that would give me that it's going to be at 432 feet from the ground. And after 4 seconds, we know from Elena's table, it has fallen 256 feet. So if I would subtract that away, I would be at 320 feet from the ground. So the equation or the expression that we would use for Diego's table is really saying, well, I'm going to take whatever I had from Elena's table, but I'm going to subtract it from that 576. So it's starting at 576 feet, and I'm going to subtract 16t squared. So if I didn't have Elena's table, I could still just substitute in for the time and do that subtraction and get my answer. So I don't have to finish Elena's table up to whatever number I'm using and then do my subtraction. I can just use that new expression that we just wrote. Okay, so here's the thing. Galileo, thinking he's all smart, he could see what was happening. He could see how the object was falling faster and faster each second. So he was trying to figure out what that shape would look like if he would graph that. And he drew this, and this is, imagine that this is, it even says it right up here, like hanging a rope. So you've got a rope that's hung here and here, and it would sag down in the middle. Excuse me. And he thought that that would be a quadratic function. And really, truly, this looks very similar to what a quadratic function looks like, but it's not perfect. Okay, so this part, and I know that the table looks kind of weird because like the y's kind of got squished. So for instance, this is really like 7.52 right here. Sorry, it's not supposed to be in 2 rows for your numbers. It says show that an equation does not work well. This is what our normal quadratic equation looks like. And we've written things that look just like that. When we would have something that was squared, and we'd say, oh, here's our pattern, and we're adding this many each time. So I want to be able to take this information and show that it doesn't really work for this exactly. Sorry. You can see that the table is really showing the points that they got from this graph. This is the graph that Galileo said, hey, I think this is what it's going to look like. Oh, can't get rid of that dry spot in my throat. I'm so sorry. So here's what we're going to do. I'm going to take this point right here, 0, 2, and that's right here. You guys know from all of your linear equations, all of our slope-intercept form, we know that that's the y-intercept. The y-intercept on this graph and in this table is 2. That means that the b has to be 2. So that's the b from this equation. And then I'm going to take, well, let's take just this 1 right here. It's the same as the -1. You can see that symmetry right there. So they're saying that the x is going to be 2.26. So I'm really using this ordered pair. If x, I'm sorry, not the x, the y. If the x is 1, the y is 2.26, which is saying that's right here on my graph. I know that the b is going to be 2. So if I take this equation, y equals ax squared plus b, let's put in the stuff that I know. I know that the x is 1. I know that the b is 2. All right, well, 1 squared is just 1 times a is just a. I'm sorry. Oh, and I forgot. I totally forgot. We have to put in the y number also. We have a y number because we're trying this ordered pair. We're going to see if this works. So this is 2.26. So to get the a all by itself, to figure out what that constant should be, that coefficient, I should say, I'm going to subtract that 2. So this is just 0.26. From that ordered pair, if this equation works, if I've got the right b, which I do, and I've got this ordered pair that works, a should be 0.26. Well, when I do this, let me pick another one of these. Let me pick, let's jump over here to 3. So this ordered pair is 3 and 4.70, or really just 4.7 would be fine when we're doing our work. So let's substitute in the x for that and see if this actually works. And we'll put in the y also. So the y we're saying is 4.7. The a we got right here is 0.26. The x is 3, and that's going to get squared. And we know that the b was 2. I just want to see if this works. Right? 3 squared is really 9. So I'm going to have 0.26 times 9 plus 2. And we're thinking that that's going to be 4.7. 0.26 times 9 is 2.34. And I'm seeing a problem here. 2.34 plus 2 is really 4.34, but that is clearly not equal to 4.7. Doesn't work. So even though this kind of a graph that looks close to a quadratic graph that we'll be working with, just hanging, for instance, a rope or something like that doesn't quite work. It's not quite exact. It's close, but it just doesn't quite work. So Galileo, thinking he was all smart, it just didn't really work out the way that he wanted it to. So our summary here, you can read this whole paragraph here. Galileo is said to have dropped balls of different masses, so different sizes, different weights. Mass is not exactly the same as weight, but he would drop them from the Leaning Tower of Pisa. It's 190 feet tall, and he would show that they would hit the ground at the same time. So it didn't matter if it was bigger or if it was smaller, if it was heavier or if it was lighter, they were going to fall at the same speed. Now that's ignoring wind resistance, right? If you had a feather, for instance, it's going to kind of float. That's different. But he had these different balls or different rocks or whatever that were different sizes, different masses, and they all fell the same way. And that was that model that he came up with. So because we've got this 16 times 4 squared equals 256 and the tower is only 190 feet tall. Oh, I've got this, I didn't read the rest of this, I guess. We've got a cannonball here that they recorded the distance that it fell from the Leaning Tower of Pisa, right? So at 0 seconds, it hasn't fallen yet. After 1 second, it has fallen 16 feet, then 64 and 144. We know this pattern. We saw this pattern earlier. Since it is only 190 feet tall, the next one really should be going this far, right? After 4 seconds, it should be at 256, but the tower wasn't tall enough for that. So it wouldn't even have fallen for 4 seconds. It'd be between 3 and 4 seconds when it falls. But if you graph this, if you take the time and you put that as your x-axis, that's your independent variable, and you graph it with the height, or the distance that it has fallen, I'm sorry, I should say, you get this kind of a graph. This is a graph that's going to curve upward because it keeps going faster and faster every second. Right, so that's what we've got there, and that's all on your paper. Another way to look at that same information is to look at it the other way, like how far is it from the ground? So at 0 seconds, it's 190 feet from the ground. After 1 second, it's fallen 16 feet. So it would be at 174, and then it falls another, it falls 64 feet after 2 seconds, and 144 feet. And again, you can see there's not enough space even for that last second. But if I graph it that way, this graph, now remember, this is not how it's falling through the air. It's not like someone threw it and this is following the pattern. This is just looking at time versus how far it is from the ground. And this one is going to be a curve going down, right? And that would hit, you can even see it, it hits somewhere between 3 and 4 seconds. Those two kinds of graphs are half of our quadratic graphs. So let me show you this one again. Sometimes those graphs are going to curve up depending on the situation that we're looking at. And sometimes they're going to curve down, but they will always be that same kind of a curve. Okay? So I have just a couple of things that I want you to be thinking about to kind of bring everything all together. So we have these two different kinds of functions, either the increasing one or the decreasing one. How are those two functions alike and how are they different? So both of those graphs that I just showed you use this equation, at least in part of it, right? That's 16t squared. It might be the initial height minus 16t squared to see how far it is from the ground, or it might just be the 16t squared to see how far it has fallen. Both of them are curves. They could be curving upward or downward, depending on if we're looking at how far it's fallen or how close it is to the ground. And every time that distance is increasing, regardless of if we've got an upwards graph or a downwards graph, it's still going to be increasing. So sorry, I'm going to get like quadruple bells in this video. How are these functions alike or unlike the visual patterns that we did, like with the squares or with the dots or with the sticks? All of those can be represented by quadratic expressions. Remember, quadratic means something is getting squared. And in this equation, you could, or in this expression, you could see 16t squared, right? So when we were looking at those dots, sometimes it's pretty easy to see those patterns. We were picking pretty nice, easy ones for you to see. With the falling or the distance that it's fallen or how close it is to the ground, maybe not as obvious. So we had to kind of help out with that 16t squared thing. For this last question, how are the graphs representing falling objects like or unlike? Oh, we just, I think that we were just doing that, kind of. The graphs representing the patterns are curving, right? When we're looking at these quadratics, they're curving upward, when we're talking about the falling objects and how far it has gone. Now I read the question more clearly. And we were only looking at whole number inputs, right? We were talking about time in terms of seconds. The curved downward ones, we were looking at how far they were from the ground, that kind of thing. Let me extend that so you can see it. Those graphs, and I did connect the points so you can see that curve a little bit more. They can be continuous, they can be connected, because even at a half a second, I could figure out where that would be on the graph, okay? So this is the cool down that you're doing today. I'm not going to show you the answers on this one, but it says the expression 16t squared represents the distance in feet that something has fallen, and the object is dropped from a height of 906 feet. So for number one, it doesn't really matter that it's at 906 feet, right? But it's going to be falling for 2 seconds. That would be in for the time. The time is 2, so you'd have to substitute that in. For number 2, write an expression representing the height of the object in feet after it's dropped. This one does use that 906 feet, because you're starting with 906 feet and you're going to take away how far it has fallen. So go back through the video if you need help with how to write those, but that's what you need. Make sure today that you check Schoology and let your teacher know if you need any help.